So this is a video just to review electron geometry. Now, first of all, in order to do electron and molecular geometry, you have to start by drawing the Lewis structure and drawing it correctly. That means putting dots on a central atom if it needs dots. If you don't do that, you're going to have a real hard time with geometry. There are 5 basic types of geometry, and that is what you see on this page right here. What you want to do is you want to focus on the center atom, and you want to count how many things are around that atom. Is there anything on the left, on the right, top, bottom? And we are counting everything. We are counting atoms, and we're even counting pairs of dots that are just sitting there, okay? So if the center atom has just 2 things, we say that it is linear, and the angle from one atom to the other is 180 degrees. If you have a center atom and there are 3 things, again, atoms or pairs of dots, it starts as what we call trigonal planar. I don't know if you see it, but that is a triangle, and they have 120-degree angles. If there is a central atom with 4 things, again, atoms and or dots, it starts as tetrahedral, and those angles are 109.5 degrees. If there are 5 things around the central atom, we say it is trigonal bipyramidal. And I've shown this in the classroom, but if you doubt me, go ahead and grab a model kit and test it out. What you have here is a central line. So I use one of my little sticks and I put an atom on either end. And then you have a triangle in the middle. And so if you look, you actually have a trigonal pyramid there, and you also have another one on the bottom. So we say that it is trigonal bipyramidal. It's got a triangle base. There are 2 pyramids. So bi refers to the 2, trigonal bipyramidal. And there's different kinds of angles in there depending on where you're looking. Now, the one that always threw me for a loop is what if you have a center atom and you count 6 things around it? It's octahedral. Now, I know. Oct means 8, right? Well, that seems odd. Why would you call it octahedral if there's 6 atoms? Well, if you look on this one, there is a square base. Do you see that square there? So up here is a square pyramid, and down here is a square pyramid. Now, what's cool about that is if you have, and guys, I cannot draw this, so I apologize. But if you have a square pyramid, you have 1, 2, 3, 4 faces. And on the other square pyramid, you have 4 faces. 4 plus 4 is 8, and that is where octahedral comes from. So again, these are your 5 basic shapes, okay? And again, you just look at that center atom and you count all the things around it, whether they're atoms or whether they're pairs of dots. Now, those are electron geometries. Electron geometry is where we count everything, all right? But the molecular geometry is not always the same. If you have a pair of dots, like look at this one right here. If you have a pair of dots sitting above that central atom, it acts as a giant balloon of negativity, pushing all these atoms and electrons away from each other. And so it changes the shape. So let's just take a look at how to read this chart, okay? When you're reading this chart, if you have 2 things, we say that there are 2 bonding domains. There are no non-bonding, so there's no pair of dots. And it's linear, and it's always going to be linear, okay? If you have 3 pairs and no dots, it's trigonal planar, and it's not going to change. So look at BF3. There's 3 fluorines, it's not going to change. But what if you have 2 atoms and a pair of dots? Well, if you build a model, you start with trigonal planar and you literally pull that one off. Well, what's left? It's what we call bent. And just note that that angle there is about 117 degrees. So now let's start with 4. We have a total of 4 things. Well, if you have 4 actual atoms like you have here, it's tetrahedral. What if one of those 4 things is a pair of dots? tetrahedral becomes trigonal pyramidal. And it is still a triangle, but it's a pyramid. And if you play with the models, you can see that it's not flat, like planar is flat, pyramidal is not. What if you have two pairs of dots, like in water? You take two things off and you're left with bent. Now, this is not the same bent as up here because that's 117 degrees, and this is actually 104.5. Now, these more complicated ones get kind of weird. If you have 5 bonding domains and none that are pairs of dots, you have trigonal bipyramidal. We talked about that earlier. And you can actually see the shape a little bit better. See, there's your stick and there's your triangle in the middle. Now, when you have to start removing things because you have this balloon of negativity, you remove from the triangle. And I've shown this with models. It's pretty slick. When you take one of those triangle pieces off, you literally create a seesaw with your model. If you take 2 off, well, all that's left is a T-shape. And if you take all 3 off, all that's left is linear. With octahedral, you don't ever touch that square. See how that square is in the same plane? You remove either the top or the bottom. Well, if you have to remove one of them, what's left? You have a square pyramid. If you remove both of them, you have a square planar because it's flat. Now, if you can draw the Lewis structure and if you can figure out the molecular geometry, what it actually looks like, you can determine whether or not it's polar. Yes, you can. And from there, you can determine the intermolecular forces. So let's just go back and discover how can you figure out if it's polar? Well, you have to think about tug of war. Do you have equal and opposite forces? So look at CO2. You've got oxygen pulling that way. You have oxygen pulling that way. So they're pulling equal and oppositely. So this, in this case, linear is not polar. Equal and opposite is not polar. But if you had, say, HCl, for example, we know Cl is really electronegative. Cl is going to be pulling that direction. That would be polar. Take a look at this BF3 molecule. This is also not polar. You have Fs at each one of those spots, and they're pulling equal and oppositely. Now, this NO2 ion is definitely going to be polar. You have N sitting here, and you have these O's pulling those electrons away. That is going to be polar. Those O's are going to win. If you have tetrahedral and you have 4 of the same element, it is non-polar. Because even though it looks weird and it's hard to see, those atoms are pulling equal and oppositely. And in the case of C and H, they're not even polar bonds to begin with. Now, when you have NH3 here, you've got the H's and you have these electrons sitting up here. So you have a trigonal pyramidal shape. That in and of itself is going to be polar. But the other reason this is polar is because these electrons are all pulling the other electrons toward it. So that makes it polar. You have a region where it's negative and a region of where it's not negative. So let's just review that again. Polar means somewhere on the molecule it's positive and somewhere it's negative. Bent is always going to be polar because you've got something up here pulling and these things pulling, and they're not pulling equal and oppositely. Okay. Trigonal, bipyramidal. Now we start to get a little bit odder. Believe it or not, that is not polar. And that's because you've got the linears pulling, and then you've got this triangle, and they're also pulling equal and oppositely. So it winds up not being anything. When you look at seesaw, it's definitely going to be polar. And if you take a look at a model, it makes more sense. T-shape, because you've got these 90 degrees and 180 degrees, it's going to be polar. But if you remove all 3, you get linear, and it's not going to be polar. All right, and you could probably do the same thing down here. That's probably not going to be polar. They're going to be pulling equal and oppositely. This one is definitely going to be polar because you have that pyramid going on. And anytime you have a pyramid, it's going to be polar. And here you've just got a square planar. And as long as they're all the same elements, it's probably not going to be polar. But if you had like 3 F's and an H or something weird, yeah, it's going to be polar. So you're just looking for, is there a region of positive, negative? Polar is going to be an unequal tug of war. That's what polar is. So you're asking yourself, is there an unequal pulling going on? If there is unequal pulling, it's polar. So from there, you can decide what intermolecular forces there are. If it is not polar, the only thing it has is London dispersion. If it's polar, if there's regions of positive and negative, then it is polar, and it definitely has a dipole-dipole moment. Think about what this means. Pole refers to the positive, negative. Di means there's two different regions. One's positive, one's negative. Now, remember, everything has London dispersion. So if it has dipole, it actually has both. The third one is the hydrogen bond. Well, you have to ask yourself, is there a hydrogen and is it attached to FO or N? Remember, hydrogen bonds are fun, spelled FON. If there's an H attached to FO or N, then that molecule will form hydrogen bonds to another molecule if that molecule has an electronegative atom that has some electrons that hydrogen wants to hook onto. And don't forget, if it's got hydrogen bonds, it also has London dispersion and dipole-dipole. So if you can draw the Lewis structure, you should be able to determine the electron geometry. You should be able to then go to the molecular geometry, and you should be able to ask yourself, is there a region of positive, negative? If so, it's polar. And from there, you should be able to determine what intermolecular forces there are. I hope that helps you a little bit. As always, you can ask for help in class, email me. I'm here for you. Hang in there, you guys.